All right, hello. I first want to thank Tim and Evan for putting together such a wonderful symposium. I'm excited to be here and talk a little bit about and provide a little bit of a unique flair on what we mean by precision imaging in the neuroendocrinology space, and specifically sort of capturing new ways of capturing dynamic endocrine modulation of the nervous system. So we're all human brain mappers. We're interested in understanding how 86 billion neurons work together to lay the foundation for the mind and drive complex behavior, a moonshot of a question, which oftentimes leads us to really focus specifically within the brain and forget that it works as part of a larger integrated system. And a key point of that or a key example of that being the sort of relationship between our endocrine and our nervous systems. And so you'll see a primary hormonal feedback loop on the left here. And maybe you've heard of sex hormones before in various contexts: estrogen, progesterone, testosterone. They are primarily secreted from our gonads. They circulate throughout the blood and bind to target receptors throughout cortex to really coordinate a lot of neurophysiological processes outside of traditional reproductive behavior. So that's really important to consider. And sex hormones indeed are powerful neuromodulators. They can influence the architecture of our brain, change the function of our neurons. They influence structure. They can regulate brain morphology across species. And they play a really significant role in shaping cognitive and behavioral processes such as memory and attention and mood disorders. So to give the laundry list of what hormones do, immediately what comes to my mind is, well, what happens when these change, when they go online, when they go offline, when they're rhythmic? And so that's sort of the question that I try to tackle in my work. And indeed, a central feature of the mammalian endocrine system is that hormones are not static and they fluctuate throughout our entire lifespan. So this is just one example of the dynamic nature of ovarian hormones across the female lifespan. And you'll see very rarely, for the majority of our life, these hormones are ebbing and flowing. And again, this is a canonical depiction of hormones too. There's a lot of individual variability in that. And if we zoom in a little bit and we just look at, say, the menstrual cycle, which is a 25 to 32 day cyclical feature of within females, we can see that, yeah, typically on average we have a similar hormone profile, but look at the error bars and look at the individual variability there. And so there's two important points to that, which is hormonal profiles vary significantly both within and between individuals, and how our brain responds to hormonal change differs. But these are not really easy things to study. It's not a 4-day experiment. And so what we tend to do is bring people in, this is an example of the menstrual cycle. We can do this throughout the lifespan and do sort of more snapshot approaches to understand how low or high hormone states really influence the brain. But it really has a call to action for, we need more precise research on sex hormone regulation of the human brain. And, we were really inspired when I started graduate school by the My Connectome Project and the Midnight Scan Club and said, why don't we also flip this classical model and start to build designs and study people over and over and over endocrine states to get at this sort of variability. And so that's what I'll talk about for the remainder of my talk, are these sort of 4 pilot studies we did over the last 5 or 6 years to try and understand the tight coupling of the endocrine and nervous systems. You might be familiar with 23andMe. It's been out for a while, but our first sort of question there was, how does the brain respond to day-to-day changes in hormones over the menstrual cycle? And so I volunteered to undergo brain imaging and blood draws every 24 hours for 30 days to begin asking this question. And what we found was quite interesting. So on the left here is just my hormone profile over my cycle. I'm glad that it's pretty textbook. You see the ebb and flow of estrogen and progesterone. And we're able to capture all of that in relation to the brain. And our first question was, do day-to-day changes in hormones influence, a very common brain function measure we look at, such as functional connectivity? And we saw really interesting patterns. So as estradiol rose across the cycle, we saw increases in functional connectivity. And interestingly, we sort of saw a different relationship when we looked at progesterone. So as progesterone rose in that second half of that cycle there, we saw negative associations with functional connectivity across the cortex. But these studies are really good for looking at more in a time-lagged way to try and understand directionality. We looked at this in several unique ways too, where we then moved over to network dynamics and looked at how do these hormones influence network connectivity across large-scale brain networks. And we found that for a variety of these networks, that estradiol was able to predict and drive network connectivity across. I'm showing the default mode here, but we also saw it for the dorsal attention network and the frontal control network. And you can see just from the model fit there that this is largely driven by ovulation. And that was really interesting to us, but we wanted to zoom in a little bit more and toggle that spatial temporal parameter and kind of look at this in a way to ask where and when is this happening. And so we used measures from dynamic community detection and studied network flexibility. So a sort of estimate of how often a node will switch its affiliation with a various network or community, a hallmark of reorganization. And what we found here on the top are my hormone levels, and at the bottom is network flexibility color-coded by the network it belongs to. And I really like to show these just stacked on top of each other because you see there's a good amount of stability over the cycle, but there was 2 significant reorganization events where there was a greater degree of flexibility, and those were intimately tied to when my estrogen levels were changing. So from that, we sort of concluded within myself, at least, that intrinsic fluctuations in sex hormones shape the brain's functional architecture. But a natural next question is, okay, well, what happens when we muck around with those hormones in that hormone profile? And can we test this again within myself? And there's sort of really easy ways to do that. To ask the question of what happens to the brain when we suppress endogenous hormones. You can do this by being on an oral contraceptive, and that's what I did. And so a year later, completed the same protocol under a different hormonal profile. And on the left there, you'll see that the hormones somewhat look sort of the same. Estrogen was able to fluctuate a little bit, but endogenous progesterone was suppressed by 97%. And so we were able to do a kind of interesting retest. We found the same relationships with estradiol, being positively associated with functional connectivity across the whole brain, able to predict connectivity across several brain networks. But I think that perhaps the most interesting thing to me was when we compared brain morphology. And so Caitlin Taylor did an analysis of, we took high resolution images of my medial temporal lobe every single day too, and she looked at gray matter volume within these subfields. And I'm going to specifically focus on CA2, 3, and entorhinal cortex. And you'll see here that if you split that data by phases, so the first 15 days of low progesterone and the second 15 days of high progesterone, you see significant changes in a subfield-specific way, which is interesting in and of itself that there are these sorts of changes tied to hormones. But once I took progesterone offline, we saw a lot of stability within those subfield volumes, which is quite interesting to us. So again, we sort of conclude that subcortical gray matter is exquisitely sensitive to hormone fluctuations, which fits within the larger cross-species literature. We are also interested in other periods of rhythm, including the sort of diurnal rhythm that both sexes have, but it's predominantly studied in males. And so we had a male come in and be scanned 40 times over a 30-day period, both at 7 a.m. and 8 p.m., so not necessarily midnight, but quite a feat. I did marry him, so it's okay. And we asked the questions of how do diurnal hormone patterns shape the brain in a male? And so you can see on the left here, very classic ebbing and flowing of hormones within a single day, about a 70% decline across most of these steroid hormones, really especially for cortisol. And we can ask similar questions. We can ask, how do these hormones relate to functional connectivity? You can look at cortisol, testosterone, estradiol. You see largely the same sort of relationship, higher hormone states related to whole brain connectivity. This isn't necessarily a new finding. We know that there are time of day effects. We know that this is yoked to our rhythms just from morning to night. But these sorts of data sets, and this is all publicly accessible, we can start to dive in more, which is what we're doing, to ask, if I had a day where I had a less dynamic range of hormones, do I see that pronounced in the brain? How do my sleep metrics or my movement or my physiological measures relate to this? Especially sort of interesting when we think about that dynamic range range of hormones changing as we age too. So he was in his 20s and showed, quite a bit of change between morning and night, but as we age, that decreases quite a bit. So it's important to look at this kind of across the lifespan. And so, we found significant relationships between steroid hormones or time of day and brain function and structure, which I didn't get into, but very interesting to us. And I'll end kind of with our latest work, which, sort of shifted this to a different time period, a different endocrine state of quite different from the menstrual cycle, which is that of pregnancy, where we can ask, how does the brain change over the 40-week gestational period? And so we know from animal and human models that pregnancy is a period of neuroplasticity. It's a critical period of brain development itself. And we also know that there's significant and persistent reductions in cortical volume and thickness observed via sort of these coarse timescales over pregnancy. Typically, again, we do a snapshot approach of comparing the brain preconception and again postpartum. And up until 2024, that's sort of all we had. No one had really studied the brain throughout pregnancy, even though this is one of the most important physiological periods of our time. And so we decided once again to just ask the question, why don't we start with a single person and densely sample them over pregnancy? And ask, how do these reductions change? What does this look like over that period? And so we scanned a first-time mom, preconception through pregnancy into 2 years postpartum. And again, the hormone changes you experience in pregnancy really dwarf the menstrual cycle. We saw 1,000-fold plus rise in steroid hormones over pregnancy. Again, not unexpected, and you see that really sharp decline in the postpartum. And pretty much we saw massive, widespread neuroanatomical change from preconception through postpartum. On the left panel there, you see reductions in gray matter volume and thickness, and on the right, you'll see sort of increases in ventricle size and cerebral spinal fluid and white matter microstructure, with birth really serving as an inflection point. If we zoom in and we just look at gestation itself, which was sort of the novelty here, you see widespread reductions in gray matter volume across most of cortex. There's very few areas of the brain that showed no impact, and the darker regions there showing the greatest impact. And you can look at this, and whatever brain region you want, the pattern is largely the same. It's this beautiful linear decline over the trimesters. Important to note that this doesn't necessarily rebound right away in postpartum, and that includes the 1 year, 2 year scan. You don't go back to your baseline levels. And I just want to highlight that, we don't stop just at one person here. This is Hannah Grotzinger's work, where they have now a lot more people that are doing this protocol, and I'll talk about that in a second. But you see a lot of replicability here in that sort of linear decline in those first 3 subjects. The 4th subject there is a non-pregnant control. But what's interesting here is that that rate of recovery in postpartum differs quite a bit per person. We also saw nonlinear increases in white matter microstructure. So on the left there, those are the tracks we're highlighting that showed an impact of pregnancy, and then just kind of demonstrating that pattern over the trimesters with the 2nd and 3rd trimester inflection that we need to replicate, because this is sort of a new finding. People didn't see any sort of changes in white matter microstructure when they did pre and post scanning, but perhaps that's because the changes occur during pregnancy and go back to baseline. So this is, again, a part of a larger project. This was sort of a proof of concept study that said, look, we need to be looking at this, and we can do this safely, and it's really important. And it's a part of a larger global initiative of the Maternal Brain Project, where there's now 13 pregnant women who have gone through this with their non-pregnant partners at the same time, and pairing that dense sampling with, mood and cognitive assessments and multimodal imaging and blood serum to look at hormones, immune function, proteomics. It's a really interesting project. I encourage you to check out the posters that I think are now done, but if you want to follow along. And again, all of this data will be open access, every single thing. So there'll be a lot there. And I just want to end by saying I'm constantly thinking about what are the right designs for the questions I'm wanting to ask. And I think these sort of focus studies can help us discover precise details of that brain hormone connection in ways we would never be able to do in these sort of big data or sparser sampling designs. And they can really be leveraged to help us understand what questions to apply to the masses. But of course, we need to work in parallel with these bigger data approaches. But with these sort of focus studies and getting a lot of data in a smaller subset of people, we can start start to do things like precision functional mapping and try to look at early neurobiological markers of disease risk or disorders like postpartum depression, which is really important. So I'll just end with my acknowledgments to thank my PhD advisor, Emily Jacobs, who I did this a lot, worked a lot with on this, and open to questions.
Hey, that was awesome. I actually was not aware of that data set, and so I'll be looking that up. I was wondering if you had thought about or had looked at the connections with mood. I'm thinking about, there's a lot of evidence now that SSRIs work through proliferation of new neurons in the hippocampus. And so I was intrigued by the volume findings there, and if you had looked within yourself without trying to get too personal, or
it's all open. It's very open book.
Anyway, so there seems to be a connection there. I was wondering, with the allopregnanolone story, if there's a connection through the hippocampus that you'd thought about or looked at.
Yeah, so this sort of hormone-mediated changes in the hippocampus and how it relates to mood and mood disorders, especially hormone-mediated mood disorders, is a really important question. We didn't do as much of that within just myself because of the single subject design, but I think that's where we need to go, and we need to say, and look at, is someone's hippocampus ebbing and flowing a lot more than others, maybe in relation to progesterone, and that's why they might have more significant mood changes over the cycle, and maybe someone else has no impact, or hormones have no impact on the hippocampus itself. I think that's the question we need to look at in more people who have varied responses to hormones in relation to mood. So, and we know the hippocampus is important for not only depression, but also it's one of the most hormone-mediated structures across mammalian species. Yep.
Great, thanks.
Any other questions? I do think it would be amazing. To me, it seems like you could recruit somebody who has had previous pregnancies where they did experience severe mood swings, and there's some expectation that they would, in subsequent pregnancy, they would experience something similar, and then you could track within that person. There's so much opportunity here.
Yeah, I will plug my advisor, Dr. Sheila Shanmugam, is thinking about that almost from the other perspective of looking at changes across the cycle from the follicular to luteal stage, and looking at the delta of brain function or structure there in susceptible women to see if the changes from preconception to postpartum are then the same, or if you can use preconception markers so we can get early. But it'd be great. We actually don't even have data really on multiple pregnancies yet. We're still at first-time moms, so lots to do.
Lots to do. Very exciting. Thank you very much.